Good morning. In the previous class, we have seen the steady state analysis of the two area low frequency control, where we have seen the two parameters change, which is change in frequency and tidal power. So when the step disturbance occurs on a system in terms of load change, how the frequency is going to be vary and how the tidal power is going to vary and how they are going to settle at a steady state at a t tends to infinity. So that we have seen in the previous class. So there also we have seen, if you have considered two identical areas, okay, if the load change occurs only in area 2, so how it will be the scenario. So we have seen these specific cases in the steady state analysis of the two area low frequency control. So at the same time, you need to study the dynamic behavior of the two area low frequency control when any disturbance occurs in a system. Okay, so anyhow the block diagram remains the same. We have developed previously block diagram for a two area low frequency control that remains the same for any analysis. So today we are going to see the dynamic analysis. So dynamic analysis means when the disturbance occurs on a system. So disturbance means here that will be in terms of the load change. When the load change occurs on a system, how the frequency, that is change in frequency, and this change in tidal power, they are going to vary from time to time. So from time t is equal to 0 to t is equal to infinite. So that we are going to see in the dynamic performance of the two area low frequency control. So for our ease of analysis, the same assumptions which we have made earlier that we are continuing here also. Here we are taking Kg into Kt is equal to 1. Means by adjusting the linker mechanism, we are having linker mechanism speed governor system. So by adjusting the linker mechanism such that Kg into Kt is equal to 1. So for both the area we are considering the same assumption. Kg1 into Kt1 is equal to 1. Similarly, this is Ksg2. Ksg2 into Kt2. Ksg2 into Kt2 is equal to 1. So these two can achieve by adjusting the linker mechanism. Okay. So at the same time, we are considering one more assumption, so which I have seen this also earlier. Tsg is equal to 0 and Tt is equal to 0. That is time constant of the speed governor and time constant of the turbine. These are considered as to be 0. Why means these are very much negligible when compared with the time constant of the power system. Okay. We are also saying that the time constant of the power system is in the range of 20 seconds. The time constant of the power system is in the range of 20 seconds, while these two are in the range of 0.2 to 0.5 seconds. The time constant of the speed governor, time constant of the turbine, these two are very much negligible when compared with the time constant of the power system. So that's why for our ease of analysis we are considering this Thg and Tt as 0. Okay, so why these are designed like this? So this having this specific reason, if there is any disturbance occurs in a system, whether the load is increased or load is decreased, the first component which need to respond is the speed governor. Okay, first speed governor need to respond accordingly, whether the generation need to be increased according to the load requirement, okay, whether generation need to be reduced according to the load requirement. So that's why the speed governor need to be respond first. So after that only the turbine will respond. Later the generator component is going to be respond. Okay, so this is the sequence of operation. So likewise we have to set the time setting for the each component in the power system. Okay, so this is the reason why we have maintained the time constant of the speed governor and turbine are very less compared to the power system. Okay, so here also in mathematical analysis, for our ease of analysis, we are considering these two Tsg and the Tt as 0. Okay, so with these assumptions, we have the block diagram we have drawn already. With these assumptions, these two blocks are reduced to 1. Kg into Kt as 1, Tsg is 0, Tt is 0. So therefore, these two blocks are reduced to 1. Okay, at the same time we are considering for the uncontrolled case. We are considering the analysis for the uncontrolled case. Therefore, delta Pc1 of s is equal to 0. So for the area 2 also, the delta Pc2 of s is equal to 0. Okay, uncontrolled case. So here also the Kg into Kt is reduced to same 1. Kg into Kt is 1. For area 2, Kg2 into Kt2 is equal to 1. Tsg2 and Kt2 are 0. So therefore, these two blocks are reduced to 1, and then there will be no summation symbol here. Okay, there is no summation symbol here. So by using this, you have to write the expression for delta F1 and delta F. So delta F1 of S you can write as KPS1 by 1 plus STPS1 into delta Pg1 minus delta PD1 minus delta P type 1 2. Here the minus will be there. Okay. Here also. So with that expression, we have written the expressions for the change of frequency delta F1 of S minus KPS1 by 1 plus STPS1. This is delta Pg1 of S. This is delta Pg1 of S. Okay. You are taking minus common. Therefore, minus delta Pg1 of S minus delta PD1 minus delta P type 1 2. If you take minus S common, so minus KPS1 by 1 plus STPS1 into delta Pg1 of S plus delta PD1. If you are writing in terms of Laplace, you can write. Okay, the delta P type 1 2 of S. So this is the expression we are obtaining for delta F1 of S. So in place of this delta Pg1 of S also, we can replace it with delta F1 of S by R1. Okay, delta Pg1 of S you can replace it with minus delta F1 of S by R1. Okay, so that's all we have directly substitute here. Similarly, for area 2, the change in frequency delta F2 of S, so same variables. Okay, just you are representing with the area 2 notation. So minus KPS2 by 1 plus STPS2 delta F2 by S. So actually in this place, this is delta Pg2. Okay, minus delta Pg2. We have taken minus S common. So if you have taken minus S common, this will be delta Pg2 minus delta PD2 minus delta P type 1 2. So that will be the scenario. When you take minus S common, delta Pg2 plus delta PD2 plus delta P type 1 2. So in place of delta Pg, we are told already delta F by R. If it is for area 1, delta F1 by R1. If it is for area 2, delta F2 by R2. So you can see from the previous analysis also, delta Pg is equal to minus F1 by R1. Okay. Why means for the uncontrolled case only. You have taken the delta P of S is equal to 0. The two blocks are reduced to 1. So directly you can get delta Pg. This is 1. So similarly for delta Pg2 also minus delta F2 by R2 in case of area 2. Okay. We are considering both the areas are identical. Okay. We are considering both the areas as identical. So identical means inverse term. So both the parameters will remain the same for area 1 and area 2. The parameters considered are expected to be same. So KPS1 is equal to KPS2. Both are equal and it is replaced with the KPS. Both KPS1, KPS2 replaced with the KPS. So similarly, TPS1 and TPS2, these are replaced with the TPS. Okay. In both the areas, you have to replace with the common notations. So again, delta P type 1 2 is equal to minus delta P type 2 1. So actually, delta P type 2 1 is equal to minus A12 into delta P type 1 2. When A12 is equal to 1, when A12 is equal to 1, why A12 is equal to 1? So A12 is equal to 1 will be arrived when you are considering both the areas as identical. Okay, so when you are considering both the areas as identical, A12 will be replaced with the 1. Okay, so how this A12 is equal to PR1 by PR2, rating of the area 1 by rating of the area 2. Okay, we are considering both the areas as identical, therefore PR1 is equal to PR2. We are considering base value for both the areas as the same, therefore A12 is equal to 1. So same one we have replaced here. So similarly, R1 is equal to R2 is equal to R. Okay, speed regulation constant. B1 is equal to B2 is equal to B. That is a motor load parameter with respect to frequency. Okay, so with this assumption, if you readjusted this expression, we are adjusting the expression, this delta F1 of S by taking S common, delta F1 of S is equal to, we are taking delta F1 of S is common, 1 plus KPS1 by 1 plus STPS1 into R1, the remaining will be that side. Okay, delta PD1 plus delta P type 1 2 into same minus KPS by 1 plus STPS. Okay, if you take the LCM, so this is very simplest mathematical modeling. Just take the LCM. This will be the denominator. Okay, after taking the LCM, you will get this expression. Okay, just take the LCM. 1 plus STPS into R. If I replace R here only, then KPS by R. So 1 plus STPS will get cancelled. So minus KPS into delta PD1 plus delta PT12 by 1 plus STPS plus KPS by R. Okay, so you have direct expression for delta FR. So same way, direct expression for area 2 also. Okay, delta F2 of S is equal to minus KPS. We are considering KPS as same for both areas. So that's why here also this term KPS as KPS. So previously it was KPS2, now it is replaced with KPS. Minus KPS into delta PT2, delta PT21. Actually here the term is delta PT21. Delta PT21 is the island power which is flowing from area 2 to area 1. So that is minus of delta PT12. We are showing here. Okay, delta PT12 minus. So remaining as this. So 1 plus STPS plus KPS by R. Okay, after rearranging you will get this. Okay, later write the expression for delta PT12. Okay, we are writing the expression for. So these two are the expressions for change of frequency. Okay, this is the expression for change in tidal power from area 1 to area 2. So we know this is 2 pi T12 by S, where T12 is the synchronizing quotient. Okay, 2 pi T12 by S into delta F1 of S minus delta F2 of S. So this expression we have derived in introduction class itself. Okay, delta PT12 is equal to 2 pi T12 by S into delta F1 of S minus delta F2 of S. So replace this delta F1 and delta F2 in delta PT12. Okay, so rotations has been changed here. Okay, substitute here, and after replacing you have to bring the expression as in the form of a quadratic expression. In the denominator you have to bring as in the form of quadratic expression. Okay, S square plus 1 by TPS plus KPS by R TPS into S plus 4 by T12 into KPS by TPS. So remaining no need to bother. Why means the status of the system can be studied by studying the roots of the characteristic equation. Okay, roots of the characteristic equation of a given transfer function. Then no need to bother about the numerator and the remaining constant. Okay, so these two parameters no need to bother about those two parameters. Just study the characteristics of the roots of the characteristic equation. Then you can find so how will be the behavior of the system. Okay, so here the characteristic equation is the denominator of the delta PT12. Okay, so for studying the behavior of the system, find the roots. S12 is equal to, you can write the expression as minus alpha plus or minus root of alpha square minus omega n square. Okay, so we know roots. You can write this S12 is equal to minus b plus or minus root of b square minus 4ac by 2a. So this is the generalized expression for finding the roots of a quadratic expression. Okay. So similarly, you have taken this 2a separately. So this one you can write as minus b by 2a plus or minus root of b square by 4a square minus 4ac. So 4ac divided by 4a square. So that's what we have written here. Okay, when you separate, the first term is minus alpha plus or minus alpha square. Okay, alpha square b square by 2a square is 4a square minus 4ac by 4a square. So 4ac by 4a square will be the omega n square. So these are the roots of the characteristic equation for a given transfer function. Okay, so within this we need to study the behavior of the system depending on this parameter. Okay, we will be having anyhow the three cases. So first we will learn what is alpha and omega. So alpha will be 1 by 2 into 1 by TPS plus KPS by TPS into R. When you write the roots of the characteristic equation, this is the characteristic equation. But this will be B. This is C. So when you replace these two here, when you replace, learn A. A will be the one. AX square plus BX plus C. For a given quadratic expression, AX square plus BX plus C. Okay, so you can write the roots as minus b plus or minus root of b square minus 4ac by 2a. So same wise we are representing here. Here this is a, b and this c. So this entire thing will be the b, this entire thing will be the c. So after substituting a, b, c in this expression, you can write a variable alpha as 1 by 2 into 1 by tps plus kps by tps into r. Okay. So when we substitute kps as, what is kps? Kps is 1 by b and kps is 2h by b into f naught. So these terms we have derived in the generic load modeling itself. So when you substitute these two terms here, okay, in this expression, you will get like this. So f naught into 1 plus b into r divided by 4h r. So take out the common r variable. So 1 by r plus b divided by 4h. So at the same time, omega n also you can write. This is t, root of 4 pi t1 to kps by tps. Root of 4 pi t1 to kps by tps. So we are going to study the behavior depending on the roots. When alpha is greater than omega n, that is b square minus 4ac is equal to 0. So you are going to study the behavior depending on when b square is greater than 4ac, b square is equal to 4ac, when b square is less than 4ac. So these are the three scenarios which can occur. Okay. So within these scenarios, how the system going to be respond for a disturbance occurs in the system, that we are going to see here. So when b square is greater than 4ac, that is when alpha is greater than omega n. Here, when alpha is greater than omega n means the roots will be positive roots. So therefore the system will be overdamped. Okay. When the variable alpha is greater than omega n, the roots will be positive, then the system is overdamped. When you consider alpha is equal to omega n, system is critically damped. The system is said to be critically damped, means we will be having only minus alpha, we will be having only one root. Both roots are equal. When alpha is equal to omega n, this term will get vanished. Second term, s1 is equal to minus alpha. So both the roots are identical. So in this scenario, you can say the system is critically damped. Okay. At the same time, the third scenario, when alpha is less than omega n, when the first term alpha is less than omega n, you can say the roots will be negative. Okay, you will get here the roots will be complex. You can say within the root you will get the negative term. So the roots will be complex conjugate numbers. So alpha is less than omega n. You can write this as S12 is equal to minus alpha plus or minus omega d, that is damped frequency, damped angle, you can say angular frequency, damped angular frequency, which is nothing but omega d is root of omega n square minus alpha n square, means you are taking the reverse of this, negative of this internal term. So that is represented with omega d. Okay, you can say WD or omega d, which is a damped angular frequency, root of omega n square minus alpha n square. So these are the three scenarios. Okay, from this, the conclusion you can derive is the system is strongly dependent on alpha. We have seen. Okay, in the three scenarios, the system is strongly dependent on alpha value. So that's why alpha is here. It's dependent on R value. Okay. Okay. The system behavior is strongly dependent on alpha, and this alpha is strongly dependent on R. So from this expression you can express. Okay. Alpha is strongly dependent on R. So when the R value is very less, there will be high damping is obtained. When R is very less, alpha is very high. Generally, this B value is very, very small compared to 1 by R. Okay, in practical system, the B value will be very much small compared to 1 by R. Therefore, there is a negligible effect of B on the response of the system. So therefore, alpha is directly proportional to 1 by R. For low values of R, alpha will be very high. Okay. So therefore, the system is said to be highly damped. Next. So as I told already, when B is very, very less than 1 by R, effect of B and damping is negligible, which is very much negligible. Next, for high value of R, this is low value of R. For high value of R, okay, you can consider theoretically as when R is infinite, where R tends to infinite, alpha value will be 0. Alpha value will be 0. So at that time when alpha is 0, then S12 is equal to this scenario. Alpha is 0, then omega d is equal to omega n. Damped angular frequency is equal to the natural frequency. Omega n is natural frequency. When alpha is 0, then natural frequency is equal to the damped angular frequency. So therefore, the system will perform undamped oscillations. Okay, the system will perform undamped oscillations. So finally, you can say the R parameter plays a very vital role in damping of the system in an interconnected system. Okay, so this we need to identify. The R parameter plays a very major role in an interconnected power system. Okay, so this is the behavior which we need to observe in case of a two-area low frequency control for studying the dynamic behavior of the system. Summary: we have studied the dynamic behavior, or you can say dynamic response. In which parameter? The dynamic response of the change in frequency as well as change in tidal power. So these two parameters we need to observe. The change in frequency and the change in tidal power are studied, okay, by taking proper assumptions. Okay, so we have developed the transfer function for tidal power. We have developed a transfer function model of a tidal power, and we have studied the response of a system depending on characteristic equation. Okay. Depending on the characteristic equation. So we have found the roots of the characteristic equation. So then we have studied the roots in three different scenarios. When alpha is greater than omega n, when alpha is equal to omega n, when alpha is less than omega n. So these scenarios we have seen. When alpha is greater than omega n, the system is getting overdamped. When alpha is equal to omega n, critically damped. So in this scenario, the nature will be sluggish in nature. So generally, these two scenarios are not suggestible for any system. Okay. Then we have concluded that the R parameter plays a very major role in an interconnected power system for the dynamic response of a two-area low frequency control. Thank you.